Garbage. Not a very compelling word, yet here I am, and here you are. The person from the production asked me if I'm going to use sound in my presentation. I said that the only sound that will be is the screams of the audience. It's the first time for me in JFOL. I'm very excited to be here. I'm Haim Yadid. I've been doing software development since I was 12 years old. That was a long time ago. I happened to discover that it is profitable hobby, so I started my professional career a bit later. And I've been doing several roles as software developer, engineering manager, software architect, but I also, 8 years of my career, I invested in doing performance optimizations and tuning. I was an independent consultant and was helping companies to solve their performance problems, including their garbage collection issues. I'm one of the organizers of the Israeli Java user group, ILJAG, and recently also a Java champion. In the last 6 years, I've been helping to build the engineering in Next Insurance. It's an insurance startup, which has, when I joined, it was only me as a developer, and now it has like 850 employees and over 250 engineers. In my personal life, I'm married, I have 2 adult daughters, and also a dog named Mushu. He's named after the sidekick figure in Mulan movie. Not the second one when they ruined it, the first one that was a long time ago. So today we're going to talk about the birth and the death of objects. It's not tragic, it's not happy, it's just what it is. And the focus of the talk is going to be about your applications. Mainstream applications with web app latency, few hundred milliseconds now and then is not a tragic event. And we will hopefully get to a position that we will start to understand how to monitor and tune garbage collection for these applications. We are not going to deal with high-performance computing, high-frequency trading, huge heaps of terabytes. That's a different story. Ultra-low latency, also not going to be discussed today, and no allocation paradigms is also out of the scope. So what I'm hoping to do is to build up some kind of common language. We're going to talk about terminology in the beginning. Then I'm going to discuss what is the current garbage collection algorithm status on the JVM. Then we're going to get into some discussion about how to monitor, which is the most important part of it, and how to solve common problems. So let's talk memory. Memory, where your data is stored, there's also memory for code, consists of mainly 3 parts. I'm not really accurate, but that's the gist of it. Static memory, when all your static variables exist. Thread stacks, and a big pile of objects that is called the heap. This heap is a very complex graph of objects referencing one each other, and the garbage collectors need to understand, figure it out what's happening there in order to free up memory. And when we're talking about memory management, we have 3 participants that are involved in this scheme. The first one is the allocator. That's the mechanism that allocates the memory. The second one is called the collector, the one that cleans up the mess. And the third one is you. Don't get offended, it's not really you, it's your threads. Application threads are called mutators because they're moving pointer around, they're changing things, they're creating the dynamics of the software. So they are creating all the mess, and they are called the mutators. How do we manage memory? Going back in the days, the simplest way, new, delete, malloc, free. What happens in C and C++? I had a few years developing in that manner. I don't miss it. It creates dangling pointers, memory leak, crashes, also very vulnerable to security vulnerabilities. And it also creates performance issues such that are related to fragmentation and deterioration of performance over time. Okay, so it's not fun. Let's move on from it. Second approach is automatic reference counting, or ARC. Each object has count to the number of referencing to it. Sounds like a very good idea, but it has several limitations. The first one is cycles. If two objects point to each other, you cannot release it. You need a different mechanism to release it, otherwise you get a memory leak. And the second one is related to concurrency. The fact that you store a number on every object is very limiting in terms of concurrency, because if two threads need to change references, they need to synchronize between them. So to the rescue, we have what we call the tracing garbage collector, which is an amazing mechanism that solves all the problems, like a big mother that takes care of everything. We just create objects and create mess, and she cleans up everything after us, okay? And it's amazing, it's working perfectly, and we can basically all go home. Unless you have the experience of getting stuck behind a garbage truck on a single lane when you're in a hurry to take your daughter to school. That's the experience of what happens to your application when garbage collection is not working properly. And it happens, and it's also possible that you don't know that it happened. So every mechanism that you use, every software that we use, we need to monitor and understand. For garbage collection, there are 3 KPIs, or key performance indicators, that we are interested in. The first one is CPU, or time overhead. How much time is needed for the garbage collection? How much time is going toward this mechanism that is otherwise could be used to serve your application? It's both CPU time and also wall clock time, because sometimes things are not measured exactly by CPU. We understand why later. Second is memory overhead. How much additional memory you need for this garbage collection mechanism to operate properly? It includes internal data structures that are needed, and headroom. Garbage collection needs headroom in order to function properly. If they don't have the headroom, they're suffering a lot. And the last and the most notorious are what we call pauses or latency. What is the probability that the garbage collector will interfere with the running of your application, stop your threads, and do something that prevents you from serving your customers for time that it's unexpected? Okay, pauses can be, in extreme cases, take seconds or even tens of seconds, and these things can even cause denial of service. So we have a heap. Heap consists of objects. Objects are referencing each other, but they're also they have references from outside. And the set of objects that are referenced from outside is called the root set of the application. The set of objects that are referenced from the root set, it can be reachable objects. The object that can be used, can be found a way to use them significantly. The other objects that are not reachable from the root set, or unreachable objects, are essentially garbage. They are dead, but they don't know it yet. When will they know that? Episode 9. Okay? Episode 9 is when they will know that they are dead. Oops, sorry. Oh, sorry, we are over that. It's this episode 9 now. Besides all of these, there are also empty regions that are usually connected in some kind of a list, and this empty list can be used to allocate objects, and we want to maintain a big enough regions that can be used in order to allocate memory. There are several building blocks that are used in algorithms. The algorithms that are used in real garbage collectors are much more complex and much more advanced, but let's go over the basics. The first part of most garbage collector is root scanning. What we want to do is to be able to identify the root set of the application, which objects in the heap are reachable from outside. In order to do that, many algorithm needs to stop the application because it's very hard to do it while it's running, although there are some advancement there that this can be done also concurrently with the running of the application. The amount of work needed to do this root scanning is linear with the number of threads. Okay, so the more threads you have in the system, the longer this will take. Okay, if you have thousands of threads, this step can take quite a significant time. After you have scanned the root, you're starting a process that is called marking or tracing. That's why it's called the tracing garbage collector. And you start from the root set, and you start traversing the heap, object by object by object, okay? There are certain algorithms to do that until you finish marking everything. The complexity of this is linear with the number of objects, the live objects on the heap. You don't care about the objects that are not live, okay? And you don't care about the size of the object because you only trace pointers. After you finished marking, what you usually do is sweeping. Sweeping is going all over the entire heap and trying to understand which objects are not marked in order to find the unreachable objects, okay? And this sweeping process takes the unreachable objects and adds them to a free list of objects, of memory, okay? And the complexity of this process is basically the size, the number of objects and fragments in the heap, because you jump over the objects. If you have one array, it's very easy to do this, but if you have a lot of small objects, it's harder. The main problem with the sweeping algorithm, and why we try to avoid it, is fragmentation. Fragmentation means that while we allocate and release, we are starting to get small holes that makes us hard to figure out when to place new objects, but even worse, we can try to allocate a big object that we can no longer feed the heap, even though if you sum all the small spaces, it's possible to do so. That's why there are two other algorithms that are used to overcome this problem. The first one is called mark compact. Instead of adding the unreachable objects to free lists, we just compact the entire heap, all the reachable objects up, and leave a big empty area at the end or at the beginning, it doesn't matter, okay? This is a very significant amount of work. It is linear with the size of the live set. If we have a lot of objects, we have a lot to move, and it's not just references, we need to move everything. And we also need to do something else. When we move objects around, we need to reroute the references. If you point an object and move it around, all the objects that reference to it need to point to the new place. And this is something that is very complex. It means that the application cannot run when you're doing it. So you need to stop the application, reroute all the pointers, and then resume its execution. Unless you're using very advanced techniques as memory barriers. All the concurrent algorithms that we discuss later on are using memory barriers in order to move things around while the application is running. Okay, Shenandoah is using Brook pointer, ZGC and C4 are using color pointers, but essentially it's like trying to replace the pointers while the application is running without the application knowing that it happened and without causing segmentation fault. Another algorithm that is very important, it's called the copy collector. The copy collectors is exactly what I want to do from time to time. I get tired of how messed up my house is, So I said, okay, I will buy a new house, I will move everything that I need, and leave the, the mess to the buyers, okay? Copy collector assumes that there is a relatively small amount of live memory inside the place that you're trying to collect and move everything that is live to another place, okay? It's a building block that is used a lot. The amount of work that it needed is the size of the live set, not the number of objects, the size, the entire size, because we're moving the objects themselves. Another thing that is very important for garbage collector is what we call generational collectors or the generational hypothesis. The generational hypothesis says that we are creating a lot of objects, but most of them are dying very fast. This is our working memory, like we are handling a request or we are doing some kind of a computation. A lot of objects are created and die immediately. And there is also different kinds of objects that are staying for a long time, maybe a cache or a state of the application. And trying to handle them together is problematic. That's why we try to separate them and handle each one of them separately. So basically, what we are doing, and I'm simplifying it a bit, we're allocating objects in new generation. When it fills up, we copy it to another place, like another new generation. And eventually, we are copying them to the old generation. That's a generational garbage collector. And while it makes things more complex, it has some advantages. The main advantage is that it has higher throughput. It means that it's able to clean more memory, because it's very easy to do the copy collector when you're working on new generation. Most of it is garbage, so we are copying very small amount of objects, okay? The new generation collection is shorter, and you're able, with this filter, to handle much higher allocation rate. Another thing that is important, when the heap are getting larger, we're starting to see more regional garbage collectors, meaning that they are not trying to collect all the heap at one time. They are splitting the heap into parts, and they are dealing each part separately. In order to deal with certain parts separately, you need certain memory data structures that enables you to understand what are the root set of a region. Okay, because it's not as clear as before, because region can point to a region, and it's a bit harder to maintain all this attribution. But with the death of CMS at, I think, Java 11, all of the garbage collectors are regional now, and we will see it. Okay. So let's discuss about properties of garbage collectors. Garbage collectors can be single-threaded or parallel. They can be stop-the-world or concurrent, and they can be monolithic and incremental. What does it mean? Stop-the-world garbage collector, whenever it wants to kick in, stops the application, does its stuff, and resumes the application. Okay? Single-threaded means that it's doing this with a single thread of execution, and the algorithm is single-threaded. Monolithic means that it does it on the entire heap. Okay? Monolithic doesn't mean that it does it on the entire heap, it does it at once in a single phase. Incremental means that it tries to do it in several phases to reduce the amount of time that it's stopping the application. But until it finishes, you don't have memory, okay? Parallel collectors are doing the same with several threads. Okay, same work in parallel, more workers. Concurrent collectors are doing it together with the applications. They are trying to collect memory while the application is running. So there are single-threaded concurrent collectors, and there are parallel concurrent collectors, so they can finish the work fast enough. Let's talk about mostly. Concurrent collectors are not really concurrent collectors, at least not most of them. They are mostly concurrent. That means that there are, first of all, phases that are not concurrent, they are stop the word. And there are also situations where they stop the word anyway, okay? And this is very important to understand. The fact that a garbage collector is concurrent doesn't mean that there is no pauses in the application. It means that the probability of the pauses is lower, and maybe the magnitude of the pauses is lower, but it doesn't mean that you will not experience them. And as we said before, you need to monitor it to make sure that it didn't go wrong, and now you see pauses that kill your experience of your application. In addition, concurrent collectors need to work together with the application. So there is some kind of a race between your application and the collector, meaning that the collector can lose the race. If it's not fast enough, it could get to a situation that no more memory, but he didn't finish to collect all the memory again. And instead of throwing out of memory error, it probably stopped the application and resolved the problem. So this is another situation when mostly can be mostly. Another thing that we need to understand is when do we kick in garbage collection. And basically not today. The longer we delay garbage collection, the better in terms of efficiency and throughput. The risk with concurrent collector is that if you delay it too much, you will get to a situation that you don't finish, you lose the race. So it's some kind of a game and heuristic that concurrent collector need to find a position to start collecting garbage that is not too far away and not too close in order to be the most efficient. Okay, so I hope that we are all on the same page in terms of terminology. Let's see what we have now in garbage collection in modern JVM. I'm talking about JVM 17, JVM 11, but I will also mention previous previous version of the JVM. So serial collector is a serial garbage collector. It's a serial garbage collector, stop the word, single-threaded, runs on it's not generational, it's generational, it's not regional, meaning that doesn't divide the heap into parts. It's not concurrent, and it's not mostly concurrent. And usually we use it when we have very small heaps and very low amount of resources. Maybe a container with a single CPU, maybe a single CPU if you can find such a machine, but usually it's not used and shouldn't be used. The second garbage collector, it's called parallel collector. It's similar to the serial collector, but it is parallel. It uses all the cores of the machine in order to finish the work as fast as possible. So it's compacting, it is regional, it's not regional, it's generational, because it has a new and old generation. It's not concurrent, it's not mostly concurrent, and usually we will use it when you're only interested in throughput for your application. How much time it takes you to finish the entire job and not the responsiveness and the latency of the application. Let's move on. G1, it's currently the default garbage collector, hence the most interesting. It is regional, meaning that it divides the heap into regions, usually 2,000 regions that are used. It is generational. It has a new generation and old generation and different algorithm for each one of them. It is not concurrent. It has like a pause time limit of 200 milliseconds as a guideline, but in many cases it cannot even pick up with that. And it's mostly concurrent only for the old generation. The new generation just pick up a certain regions, do copy collector, as we mentioned before, and finishes as fast as it can, but it stopped the world. It should be used for mainstream applications. Okay? Why shouldn't it use for all applications? Because for applications that are very latency sensitive, there are better alternatives at the moment if you are willing to sacrifice additional memory. Okay? Another garbage collector that is already production ready is ZGC, developed by Oracle. It is compacting, regional. It is not generational, meaning that there is no new generation and old generation. Every garbage collection needs to take into account the entire heap of the application. It is almost concurrent. It has a target of 1 millisecond pause time. And it's mostly concurrent because most of the phases and the work that it's doing is running together with the application. Similar to it, there is an algorithm called Shenandoah that was developed originally by Red Hat. Now it's supported by the Amazon Corretto team. And it works a bit differently. It was totally differently from ZGC. The implementation is totally different, but the goals are the same. Again, compacting, regional, non-generational, but there is a very advanced work to make it generational. You can see a talk by Kevin Nielsen in DevOps 2022 about this topic. Probably take some time, but it will be there. Also target pause time of 1 millisecond, and most of the phases are concurrent. Why shouldn't you use these two garbage collectors every time? First of all, in order to keep up with large allocation rates, they need more memory than G1. Because they don't have generational filter, they need more memory in order to keep up. Otherwise, you will get performance penalty. The second thing is that for a lot of applications, G1 is just good enough. Okay, you might know it or you might not know it, but if you monitor it properly, you will see that the probability that something will go wrong and it will pause for a long time is very low. So if you're having some kind, I don't know, of online store, if once in a day something will pause for a second or two or a few seconds, it's not that a big deal, okay? If you're very sensitive for performance and latency, etc., you probably want to consider C4 of Azul. You probably need to pay for it. But it's compacting, regional, generational, concurrent, mostly concurrent, and gives a very good behavior when it comes to latency and pause time. Okay. So this is what we have in current JVM version. In earlier version, we had CMS, which was deprecated and then was removed. And CMS was generational. It was not regional. It was using the Mark compact algorithm in order to compact the old generation. And in general, it was worse than G1. Okay, G1 is not amazing, and CMS is even less. Okay, so I've talked a lot of things, and I didn't help you a bit. So let's go practical, and this is the time when I put a picture from DALI. This is practical engineer Picasso style. What should we monitor? As I mentioned before, we should monitor the CPU and time overhead. We should monitor the memory overhead, or how much memory, additional memory we need in order to function properly. And we need to monitor latency and pauses. How do we do that? The best way to do that is to use garbage collection logs. And in modern JVMs, that's the way to do that. There are a lot of parameters, and probably you want to put other things, but basically I want GC, I want it to a file, I want 5 files, each one 20 megabytes, and then you want the time, uptime, level, and tags in the log. And when you have that, every garbage collection event is written into a file with a very long description that is both machine unreadable and both human unreadable, okay? So it needs some expertise in order to read it, and every garbage collection has its own nuances. But what can you get from that? Every line says what happened. For example, here, young pause, normal G1 evacuation pause, means that we were running garbage collection. And I increased the size of what is interesting right now, and what is interesting right now is when it happened. Okay, so we have an event, when it happened, what happened. Here, we were evacuating from 486 megabytes to 130 megabytes. Around 300 megabytes was cleaned, and it took 93 milliseconds. Okay? And roughly that's all that you need. If you have a concurrent collector, you need to understand what are the phases, but what can you do with that? If you have the start time and the end time of the garbage collector, and how much time it took, you can understand the overhead, the frequency. And if you understand if the phase is a pausing phase or not, you can also understand the pause time. Okay? By looking on the freed memory, you can also understand your allocation rate, how much memory you are creating, hence how much memory the garbage collector is cleaning. You can understand it from the file if you dare to read it, but you can also feed it to certain application. There is an application called GC Viewer, which can parse garbage collection logs and give you some information, such as a very nice graph. What is the max heap after GC, which is basically the state of the application, or how much memory you hold all the time. What is the throughput of your application, or in other words, what is the overhead of the garbage collection? If it goes too high, maybe over 5%, but it can go much higher. Maybe in extreme cases, it can get to 20%, and then you even can get an out of memory in such cases. It's not a good sign. You can understand what is the max pause and what is the behavior in terms of statistics over that. And basically that, a lot of other information that you get. Same with a website called GC Easy. You upload the garbage collection logs and you get it over there, and from there you can get similar things. You can also, there is also a JMX called Java Lang Garbage Collector, which can, if you catch it frequently enough, you can see all the garbage collection events there, each one of them, how much time it took, how much memory freed, and you can maybe try to do something similar to what you can find in the garbage collection logs, but it's less optimal. A lot of people are looking on the graphs of the memory going up and down and try to figure it out from that what's happening. It's very hard because the amount of used memory says nothing about the process, only what happens after you do garbage collection. There is also a plugin to Visual VM called Visual GC. It's not useful for ZGC in Shenandoah, but it's very nice. You can see memory going up, down, objects moving, different regions, etc. It's really cool. It gives you some kind of a hunch, but it's not very useful. In order to understand latency or pauses or hiccups, you can use an approach similar to a tool that developed by Gil Tennant that is called JHiccup, which basically tries to have a thread, takes a thread, which wakes up every specific amount of time, like maybe 100 milliseconds or maybe 10 milliseconds. And if it wakes up and it's not the time that he expected to be woken up, it means that we had some kind of a pause. And pauses can be from many reasons. Maybe your VM has gone down to swap, maybe someone shut down the machine, but in many cases, it's related to garbage collection because it means that a thread that is basically doing nothing cannot wake up on time and check what time is it, okay? So if you measure the difference between when you should have woke up and what's the current time exactly, you can try to have an estimate of a pause, okay? And if you do it frequently enough, you can understand what's going on with your application. In JHiccup, it's a lot of statistical work over there. They keep all the data, but you can implement a very similar mechanism in your application, a few lines of code, and get enough information to get a hunch how the pauses look in your system. In order to estimate live set, it's not good enough to look on what's happening in the heap. You probably need to do that after forcing garbage collection or using JMap to get a histogram which specifies the live set. JMap means histo, live. Or even take a heap dump and write it down, analyze it in order to understand how much memory the system is using. And the system is using memory as a state, long-lasting. If you have a generational garbage collection, this should be in the old generation. And if you have a process that is not using generational garbage collection, you have a loud state, you might have problems or inefficiencies. In addition to the live set, there is the working memory. Every request needs memory, and it's stored in the memory. But if you have 1,000 concurrent requests, the live memory that needed is high. This memory should be in the new generation. Okay, it shouldn't flow into the old generation. So this is how to monitor. Now let's try to look on certain common problems. I've written a small application. You can find it on GitHub. I'm very not proud of it. I'm planning to improve it. But basically what it does, it creates a pause detector. As I mentioned, like JHiccup wakes up every few milliseconds and tries to understand what's going on. It has a class that is called stateholder that holds 2 gigabytes of memory, a lot of objects, okay, very small objects. And it also has a class that is called brutal allocator, which allocates 500 megabytes per second and stops, and then wakes up at the beginning of the next second, another 500. And I have 2 of these. And I wanted to check what happens with this small benchmark on different garbage collectors. And to emphasize what's happening, it's not an official benchmark. It's not something that you should kill me about it because it's just a test, but it should give you some kind of a hunch. So I ran all of them with G1, with Shenandoah, and with ZGC. And this is visual VM showing the memory consumption and also the CPU usage. Any guess which one is G1? Is it the first one, the second one, or the third one? Who guesses the first one? No one. What is the difference between you see that there is an orange line, which is the CPU usage, and the 2 later have also CPU usage. Who shouldn't have CPU usage for garbage collection here? That's G1, because it has generational filter. We have a large state, and both ZGC and Shenandoah need to deal with this entire state all the time. That's why every garbage collection takes resources. It doesn't affect a lot of things that we'll see later, but it has effect on the CPU. Okay, it needs CPU in order to work. G1 just fill in the new generation and throw everything, because these objects are very short-lived. And what are the results? I was running this with a 4 GB heap for 2 minutes of execution. And I measure how many times I got pauses that are longer than 10 milliseconds, and how many times I got pauses that are longer than 100 milliseconds. I measure the average runtime for iteration. I'm allocating 500 megabytes of memory. I do it every second, and I hope that it will take shorter than 1 second, and I write down what is the average time that it takes. And of course, the live set. So G1, each iteration took 300 milliseconds. It means that it allocated memory and rested 700 milliseconds. Shenandoah took almost 800 milliseconds to complete. ZGC took 352 milliseconds to complete, and Parallel Collector took 434 milliseconds to complete, which was quite surprising because I was expecting that it will be the fastest one. In terms of live set, you see that ZGC consuming more memory. The reason that it happens is that all of the rest having some kind of optimization that is called compressed OOPS, taking 64-bit pointers but holding them in 32-bit pointers. And the ZGC cannot do that because it has a call-out point-end mechanism, so it can map regions seamlessly. That's one of the superpowers of ZGC. But for small heaps, it's a memory penalty. It needs like 25% more memory than the others. And also experienced several pauses, both for Shenandoah and ZGC. I don't think that they are significant, but it means that it can happen. And I also did so that ZGC was stalling the threads that are allocating too much memory in order to be able to keep up, okay, from time to time. If, by the way, I use 3 brutal allocators, G1 falls apart, okay, in this case. Not G1, ZGC. G1 continues to work quite well. ZGC falls apart, and the way to solve the problem is how do we solve throughput problems? More memory. If we increase the heap to 8 gigabytes, ZGC goes back to the business, okay? More memory, solve throughput problems, okay? You can just throw more memory on it. Okay, but on 4 gigabyte, it could not keep up anymore. Okay, G1 could because it had, G1 could do that because it has the generational filter. If, by the way, I remove the state, the 2 gigabyte state, and just allocate a lot of memory, this problem will not happen. ZGC and Shenandoah will be able to keep up because they don't need to do a lot of work for every garbage collection cycle. So how do we solve temporal overhead or garbage collection overhead? Increase the memory, okay? Latency. In order to solve that, we probably need to move to some kind of a more concurrent algorithm, but we definitely need to understand what are our latency requirements. If 500 millisecond pause from time to time is good for you, and you're not doing high frequency trading and you're not going to lose money for that, then so be it, okay? But if you think that you have 500 milliseconds and you don't look at it, you may discover, if you look at it, that you have 5 seconds pause, and it happens every few minutes, okay? And the application is cycling with around garbage collection without end, okay? There is another phenomena that I was experiencing in production. it is fragmentation that is a result of huge, humongous objects. G1 divides the heap into region. If object doesn't fit into a region, actually if it's bigger than half of a region, it's declared as a humongous and it takes the entire region. And if you have objects that take more than one region, they actually create fragmentation. And this fragmentation can lead to an out of memory. I'm able to reproduce it both for G1 and Shenandoah. You just create a lot of big objects, and then you release every second one of them, and then you try to allocate another big one, and it fails. ZGC seems to do better here because it's able to merge different regions to a bigger one by its ability to point from different places to the same memory place. Another anomaly that is related to generational garbage collection is what happens when the application state is going beyond your old generation. If you have objects that are part of your application state, or they are long-living and they are flowing into your new generation, that's the end of the game, okay? The garbage collector will not be able to function properly. You need to understand that this is the case. You need to understand what is the size of the new generation, what is the size of the old generation. If you are flowing out of the old generation, probably there are two ways to fix it, either to reduce the size of the new generation or increase the size of the heap so it will fit again into the old generation. And actually there is one last thing. If the new generation is too small, too many objects will flow to the old generation, which should have died before that. Okay? This is also a phenomena that is not very good, and you should be aware of that. Basically what you will see is that the heap size is always increasing until the garbage collector, or the old garbage collector, is kicking in. Okay? Relevant only to generational garbage collectors, definitely not for Shenandoah as ZGC at this point. So, to sum it up, I have homework for you. When you go back home, you can now take pictures or look at your services that you have at production. If you're able to answer at least 4 of the questions that are here, you're in good shape. Okay? If you cannot answer it, you have no idea what happens in your production system. It might be functioning poorly, and you have no indication that it is the case. So you need to be able to figure out, open garbage collection logs, look on data to understand what is the heap size, what is the GC overhead, what is the max pause time in peak time, number of collection above the pause time, because only understanding that there is a max pause time is not relevant. What is the size of the live set of your process, and what is your allocation rate? Okay? Saying that, there is a huge book about garbage collection that you can buy and read if it's not enough. Otherwise, thank you for your time.